Alright, hello, welcome to the first lecture of multivariate calculus. My name is Arkady. So the difference between multivariate calculus and regular calculus, well, multivariate calculus is an upgrade. Before you had mathematics that describes motion in one line, a one-dimensional motion. We now want to expand this and develop the mathematical machinery to describe motion in two-dimensional space, three-dimensional space, and eventually n-dimensional space, so any Euclidean space of finite dimensions. We will also explain what dimension is a little bit later. So, and a good example of this to be prepared for, and that's why the first lecture might be seemingly easy and yet must be studied with utmost care, is parametric equations. We're going to start in this chapter with parametric equations in the plane, just very basic equations of the line and equations of the plane. And the same concepts will be afterwards used to describe complicated mechanistic objects, such as one ball rolling inside of another, which produces a curve known as hypocycloid, or other type of curves of the same family. So our first lecture begins with linear space. So linear space is going to be this mathematical object which we are going to cover informally, in which those mechanistic objects such as the hypocycloid reside, in which they are described. So what you imagine is a certain point traveling in space, and suppose that this point is given some direction. So this direction is this line, right? So this is the position of the point currently as you're looking at it. And in 1 second, it will have traveled here. So that will be 1. In 2 seconds, let's take this line, and it will have traveled here. And you continue in this fashion, right? It goes to position 3 onwards. So you have 1, 2, 3, and let's say 1/2 would be 1/2 seconds. Let's say 1/2 would be 1/2 seconds from the time you're looking, and the particle is here. There is continuity of motion. So what happened 1 second ago? 1 second ago, you can imagine the particle were here. So this point is -1. 2 seconds ago, the particle was here, so it's at -2. And what you see is that with respect to the particle, you have this generated number line. So that's where the language linear space comes from. You can think of specifying a direction of motion, and that generates a number line. And you can say it's one-dimensional because a number uniquely describes relative to this line where the particle is located. So there's only one parameter, only one number that you need to specify to say where the particle is located. So we can now make the situation slightly more complicated. So suppose what you have now is another direction that is drawn from the origin. So then you have two types of motion. So the motion that travels along this line and the motion traveling along the line generated by moving a particle here. So this is 1, this is 2, similarly this is -1, -2, etc. So you have two lines. So by expanding this, you now have a grid. So in this grid, you move parallel to the red line and parallel to the black line. And notice this is not rectangular, they're not perpendicular to each other. This one does not have any specified relation to this one. This is just some other motion, some other speed. So for some applications later on, it will be necessary to understand coordinate systems that are not rectangular, but just an arbitrary coordinate system. This is, as you can see, as an arbitrary coordinate system. So for instance, this position here is 1.1. In other words, it is one motion along the black line, followed by one motion along the red line. Right? And if you know how those motions are produced, you know how to travel, in other words, parallel to the black line and parallel to the red line, you will be able to locate yourself in that space. This is a two-dimensional space. Why? Because you require two parameters to specify your address, to specify a location of a particular point. So this point can be specified as 1.1. It has to be so one along the black line, one along the red line. And you cannot specify an arbitrary address of a point in this space without at least using two parameters. Then it will be a two-dimensional space. So before we can say a bit more about those directions, just we are using it very informally, we need to introduce the geometric notion of vectors. So the notion of vector will have much more abstract definition once you progress in mathematics. But for us, we imagine that we have some space, and in that space we have a point A and another point B. So then you can imagine a line drawn from point A to point B, and you imagine starting this line at A and drawing it in the direction of B. So that's marked by this arrow. This is denoted as the vector AB. So a vector is something that has both length. It's a mathematical object that has a notion of length. So you can think of distance from A to B as the length. And it has direction. So here is A and here is B, and that's the direction. We use this notation to signify size. So that is just specifies the size of vector. We're afterwards going to develop notation to specify just purely the direction. Now notice I didn't explain what is size and what is direction. Those are primitive concepts. This is just something that you intuitively understand and use to build up this mathematics. So for instance, the size of AB is denoted like that. Later on, when we develop the mathematical description of a linear space, we will then explain how to compute the size in terms of some primitive vectors. So a vector, you should think of a vector as just the displacement from one point to another. So what does it mean? Well, suppose I take the vector again from point A to point B. And denote this vector by little a and arrow. Then I can select a similar point A prime and a point B prime. This B prime has to be selected here. and you have this vector A prime hat. Now you can say that those two vectors are the same, they're equivalent. If this point is carried to A, and by carrying the point A prime to A, B prime is then carried to B. So you can say that A is equal to A prime if by moving A prime to A, B prime is moved to B. Now, of course, by moving I mean you do not rotate it, you do not change again the annoying word, its direction. What you in other words try to express by this is that displacement is indifferent to where it is occurring. So the displacement from A to B, the point A is very similar to point A prime. The space is uniform. There is no particular importance to any point in the space. So if you have the same situation, the same type of motion, it's parallel to the motion that happens from A to B, then the two vectors are the same. So this again is something hopefully very simple. So just to make sure, let's look at a few examples. So example 1, we have here a vector A and here a vector B. So it is clear that the vector A is not equal to the vector B. What's wrong here? It looks like they have the same direction, it looks like they are parallel, but one vector is bigger than the other, so they don't have the same size. You can say the size of A is not the same as the size of B. This, by the way, is also called norm. 2. Here we have another picture. So here is vector A, and here is vector B. So here we again have that A is not equal to B. In this case, we have that the sizes are the same, but direction different. And finally, example 3, well, here are two vectors. So in this case they are the same because they have matching size, matching length, and matching direction. The next thing that we want to understand is how we add vectors. So addition of vectors. Well, again, think of displacement. So if you start at position A and you displace by some vector A to position B, and then from there you displace to position C. By some another vector b. If vectors are to signify displacement, then you should imagine that the motion that you have undergone is really the motion from A to C. So it is this motion. That should be our vector A plus B. It is, in other words, the displacement. The displacement doesn't keep track of how you shifted positions, it only keeps track of your initial position and your final position. It points from your initial position to the final position. So the displacement here is just the vector A plus B, which is this vector from A to C. It completes the triangle. Now, it's not immediately obvious that A plus B is equal to A plus C. So it's not immediately obvious. It's not immediately obvious that we would have A plus B equal to B plus A. Those potentially are different displacements. So that's the next thing what we're going to try to show. So for that, let's just draw a new diagram. So suppose we have this A here, this is B, and this is C. So we displace from A to B by the vector little a, from B to C by the vector little b. So by what we just said before, this vector here is A plus B. Right? A plus B. Now, what does it mean to displace first by B and then by A? To displace first by B means that from the location of A, I'm going to move parallel to the vector B and by the same length. So I take this vector here, and I displace like that first. So this is B first, and then from the vector B I displace by the vector A. So the total displacement makes me arrive from the point A and lands me on the point C. So what I have is B plus A is this arrow. And they are the same arrow, from the same direction, the same magnitude as A plus B. Now the reason I knew that this would be close, the reason I know that it would arrive at the position C, is because of parallelogram law. Right? So what we had to construct at A, we had to construct a line of the same magnitude as B and parallel to it. And from it we had to construct the same length as A and parallel to it. So it had to produce a closed parallelogram. And the corners of those parallelograms are, one corner is A and the other is C. So the displacement in both cases is the same. That's just a geometric demonstration, not truly a proof, but a good reason for why you should believe that A plus B and B plus A is identical. So this property is known as commutativity. If addition is commutative, you can say A plus B is the same as B plus A, which is what's happening here. Now you can see that we are beginning to develop some algebra. Just like with numbers, we know how to add 1 plus 2. We developed algebra there, right? So right now we already developed the algebra of adding two quantities. Now in algebra you also want to have the zero. So what is the zero vector? this is specified for convenience, we're going to say that the zero vector is a vector without length, or better, vector with any direction and zero length. Again, to say that something has no length is different than saying it has zero length. Zero length is a quantity, it's a particular measurement of length, whereas no length means that a length cannot be assigned to it. So by any direction is, in other words, I would like to have the property that 0 plus any vector A is equal to the vector A. So in other words, 0 is just the vector of not moving anywhere. So you might not move anywhere in this direction, you might not move anywhere in this direction. In any direction you want, you might not move anywhere. So that's what you mean by 0 can be assigned any length. Sorry, any direction. Now, we then want to also have additive inverses for vectors. So by that I mean the following. So suppose that you travel from the point A to the point B. And then you want to go back. So if you go from A to B and then from B back, then you have not traveled at all. Right? So what you have is, you have the vector A here, and you would want to have the property that A plus minus A. By minus A you would specify a vector, in other words, that has the same length, but goes in the opposite direction. So that's my minus A here. Right? A plus minus A gives me displacement of 0. Because in other words, the net motion is not moving anywhere at all. The net displacement is that I start with A and end at A, therefore I have not displaced. Another small thing that we want to establish is associativity of vector addition. So associativity of vector addition is, well, suppose I first add A and then B, and to that I add another vector C. This should be the same as if I take A and I first add B plus C. So it doesn't matter, in other words, in which order you combine the vectors. So to illustrate this, let's suppose that I have the point A, B. So this here, the dotted line, is the displacement by A. Then from B to C, displacement by the vector B, and then finally displacement C to the point D. So I travel by adding two vectors at a time. So the displacement from A to B, from capital A to capital B, is this vector here. This vector is A plus B. And then A plus B plus this vector will give me A plus B plus C. On the other hand, Just drawing the same picture more or less again. On the other hand, if I do this type of motion, then I first must consider the addition of b plus c. So that would be this vector. And to this vector, I must add the vector little a. So notice that the both motions will necessarily land you in the same point D. So that tells you that this identity must hold. So again, we covered them rather dismissively, but I hope you understand that it's going to be important. We're going to study objects in which this is not necessarily true, in which associativity is not necessarily holding. So you cannot just assume that everything behaves like your regular number system. So you have to be very careful there. Vectors are still very nice, but we're going to study matrices which are not commutative. A product of one matrix by another, if matrix A is multiplied by matrix B, is not the same as multiplying matrix B by A. And with cross product, it's not going to be associative. So again, those concepts will be developed later on. So for now, let's just see what addition of vectors amounts to by a very simple example. So you take the point A and you take this complicated route. So imagine you travel like this. So this is your vector A, this is your vector B, this is your vector C, this is your vector D, this is your vector E, and your vector F. So what is the sum? How would you draw geometrically the sum of A plus B plus C plus D plus E plus F? Well, geometrically, again, what do you keep track of? You keep track of only your initial point and your final point B. Nothing else matters. So here it is. It's equal to this. Let's call this B. Okay, this is the displacement. And just to be sure, another very simple example. If I start at point A and I move like this, so we have here A, B, C, D, and E. So what is the sum of A plus B plus C plus D plus E equal to? Well, again, what is our initial position? It's A. And what is our final position? It's A. So what is the displacement? So the displacement is just the zero vector. The net motion, the net displacement is zero. You return to the same location where you started. So again, vectors just try to capture the notion of only keeping track of initial and final state. Well, now we need to consider yet other developments of the vector. So given a real number r, so just a number r like 1/2, 3, 5, pi or something like that, how can we multiply a scalar times a vector? So first of all, r is called a scalar. So to understand what it means to multiply by the vector, consider again the moving particle. So if this is the vector a, so this is 1 times a. Now this here is going to be 2 times a. So in other words, after 2 seconds, if this is velocity, after 2 seconds the particle is displaced twice times a. This then is 3 times a, etc. So in other words, to multiply by a scalar, in this case by a positive scalar, means just to increase the magnitude. So this increased the magnitude of the vector a threefold. On the other hand, if we multiply by a negative scalar, you can think of this as moving back in time. So this is -1 times a, that would show this direction. -2 times a moves you twice from the origin, etc. So you can say that r times a is equal to the vector whose magnitude is absolute value of r. It's multiplied by r-fold times the size of a. So what this means, its size is absolute value of r times the magnitude of a, and direction so direction, you have two possibilities: a, that of a, so they go in the same direction if r is positive, b, opposite. If r is negative. So again, very simply illustrated by this example. So we are just denoting vectors for now just by drawing them geometrically. So if this is a, then minus a is just the vector in the opposite direction. So it's the same vector of the same size, but in the opposite direction. And this is the same as -1 multiplied by the vector a. Here is -1 the scalar multiplied by the vector a. So 2 times a would then be equal to this vector. You keep the same direction, but you just make it twice as long. So here is the vector, and you make it twice as long. If you multiply by the number like 1/2, you just divide the length of that vector by 2. So you just take this vector and you cut it in half. Right? And if you multiply by minus 1/2, it's just that segment, but in the opposite direction. So now we have defined addition of vectors and a multiplication of a vector by a scalar. Now, how do those operations relate to one another? So, for instance, suppose that we have a scalar k, and you have two vectors A and a vector B. So then what can you say about the vector k times A plus B? And what can you say about the distributive property? In other words, that's what we're trying to establish. What can you say about k times A plus k times B? So let's draw both pictures at the same time. So first, let's draw the vectors A and B tail to tail. So this is maybe the vector A. This is the vector B. So the first thing, when we multiply, we need to multiply A by k and B by k. So supposing that k is bigger than 1, if k is bigger than 1, then k times A is longer. Maybe something like that. And k times B is longer. So I'm sorry, this would be just so this is the vector A plus B. Maybe the vector A is here. That will be the vector A plus B. And that then will be the vector K times A plus B. So if we multiply B by k, we have this vector k times b. Now we can then draw a vector from k times b to this vector here. And we are going to then try to describe it. What is this vector? Well, this vector completes a triangle. So you can see that there is proportionalities. This side is proportional to this entire length. This is proportional to this entire length, and therefore this and that will be proportional. So this must be a scalar multiple of A. If it is a scalar multiple of A, what can it be? Well, this triangle, each side is multiplied by k, so this must be in fact k times b, k times A, I'm sorry. So this is the vector k times A. So you can now see that k times A plus k times b, adding the red vectors, those vectors here, those vectors, this one and that one, gives you the vector k times A plus b, which shows that, that those quantities are the same. So now we consider how to subtract one vector from another. So in other words, we want to calculate the following. So suppose we have A is some vector like this, and B is some vector like this. How would you calculate B minus A? We do that again right now just geometrically. So notice that B minus A is really addition of vectors. It's really B plus minus 1, the scalar minus 1 times the vector A. So it's in fact just adding two vectors. Now one way to do that is to draw A and B tail to tail. So you draw the vector A, and you draw the vector B. And then what you do is you complete this triangle. So from the tip of the arrow at A, you draw a vector to the tip of the arrow at B. And we don't know what this vector is, so let's call this vector C. So observe what happens. Observe that if I displace first by A and then by C, in other words, if I do this calculation, A plus C, the displacement A plus C is the same as displacing from this initial point by B. Therefore, doing it algebraically, if I now subtract from both sides A, so I take A plus C plus minus 1 times A. According to the laws we showed, we can first add A, we can just switch their position, so we can add it as minus 1 times A plus A plus C, and that gives us just C. But on the other hand, this equation gives us the vector B minus A, right? Because if we added minus A to this side of the equation, we must add minus A to the other side of the equation as well, and that gives us B minus A. In other words, the conclusion is that if you want to draw the displacement from the displacement B minus A, all you have to do is you take the vector B and A, put them tail to tail, and at the B vector you draw the arrowhead, you draw this line, you complete the triangle, and you just draw the arrowhead at the tip of the vector from which you are subtracting. Just to end this discussion, this basic discussion of vectors, let's just consider a few examples. Just a comprehension check. So, first question is, which is a vector? So if I take this quantity, is it scalar or vector? Well, this A is a vector because of the arrow on top of it, but you take its magnitude. So the magnitude is its size. and the size is just a number, so that would be a scalar. So which of the followings are vector or undefined? So suppose I have 2 times A plus 3 times B. Well, this means I take the vector A and I just increase its magnitude twofold. And I take the vector B, increase its magnitude twofold, so if once I add them, it's a vector. The sum must be some displacement. So if I take some vector B minus 4A, that's also a vector. Again, minus 4 times A, it's really adding to the vector B, minus 4 times the vector A. What about this thing? We haven't ever described any way of multiplying vectors. So this is undefined. In later lectures, we will consider two types of products of vectors, the dot product and the cross product. But right now, notice there is nothing here. This is just some vector A multiplied by the vector B, and we haven't defined it. How about D? Again, this is a zero vector, and this is just some other vector, and we haven't defined a product between any two vectors. So this is again undefined. On the other hand, if I have 0 times A, this is going to be the zero vector. Because what you do is you take the vector A and multiply it by the magnitude 0. In other words, you have a particle traveling with velocity A, and you ask what happens after 0 seconds. And in 0 seconds there would not be any displacement. So that's why it's natural to think of the scalar 0 multiplying any vector A, and that gives you the zero vector. So we have the vector F. If we take A divided by the magnitude of A, this is a vector if the vector itself is not 0. So if the magnitude is not 0, so that is the same way as saying the vector A is not 0. Final example. We can do this. We can take A, take its magnitude and multiply by B, minus the magnitude of B multiplied by A. So this is always a vector. It's B scaled by the size of A minus A scaled by the size of B. So that would always be a vector based on what we described. So far we only did the geometric interpretation of vectors, very basic one, and what follows will be already a bit more complicated.